Hello friends, welcome back to my channel Engineering Mathematics DJ Ganit. In this lecture also we will discuss one more problem on Cauchy's residue theorem. So let's start with this problem. We are asked to compute the integral of the function 1 over z times z minus 2 to the power 4 where C is the circle mod z minus 2 equal to 1 taken in counterclockwise direction. So this is the circle with center 2 and radius 1. So first we write down the given function. Given function is denoted by say f of z. Let f of z equal to 1 divided by z times z minus 2 to the power 4. So clearly f of z will not be analytic at points for which z equal to 0 or z minus 2 raised to 4 equal to 0, that is z equal to 2. So these are the only points at which function f of z fails to be analytic. So it is clear that these 2 points will become isolated singularities of this function f of z. So we can write that then f of z has isolated singularities or isolated singular points at z equal to 0 and at z equal to 2. Now given curve is the circle with center 2 and radius 1. For example, we can have rough sketch of the circle with center 2 and radius 1. Suppose this distance is 1, so this is 2, this is 3. So circle is a circle with center 2 and radius 1, so it will pass through this point 1 and 3. So rough sketch of the circle we can have in this way. Okay, so it is approximately look like this. So this is the given contour, which is a circle with center 2 and radius 1. Now function is not analytic at z equal to 0 and z equal to 2, but z equal to 0 is outside this contour, so we are interested in z equal to 2 only, which is inside this circle mod z minus 2 equal to 1, and our function is analytic everywhere on and inside this circle except only one point z equal to 2. So we can write that f of z is analytic everywhere inside and on a simple closed contour, C, which is circle here, except only one point z equal to 2, and this z equal to 2 lies inside this simple closed contour or inside this circle. So therefore f of z satisfies the requirements of Cauchy's residue theorem. So we can apply Cauchy's residue theorem to evaluate integral of this function f of z along this circle. So for that we need to calculate residue of f of z at z equal to 2. Z equal to 0 is outside this circle, so it will not be of interest. We are interested in the residue at z equal to 2 only. So for that we rewrite our function in another form. F of z is 1 divided by z times z minus 2 raised to 4. So this I can rewrite as z minus 2 raised to 4 in the denominator, and I consider 1 by z in the numerator. So we have f of z equal to phi of z divided by z minus 2 raised to 4, where this phi of z is 1 by z and this 1 by z is analytic at z equal to 2. this 1 by z is analytic everywhere except z equal to 0. So therefore it is analytic at z equal to 2, and value of phi of z at z equal to 2 will be equal to 1 by 2, and it is non-zero. So therefore f of z has a pole of order 4 at z equal to 2, because this f of z is written in this form, phi of z over z minus 2 to the power 4, where phi of z is analytic at z equal to 2 and value of phi at z equal to 2 is non-zero. So therefore f of z has a pole of order 4 at z equal to 2. Therefore f of z has a pole of order 4 at z equal to 2, and residue of f of z at z equal to 2 will be equal to third derivative of function phi at z equal to 2 divided by 3 factorial. So first we have to find out derivatives of this function phi of z up to third order. So now phi of z is 1 by z, so therefore phi dash z is minus 1 divided by z square. Then second derivative is minus 1 as it is. Derivative of 1 by z square is minus 2 over z cube, and here negative negative positive, so we have 2 divided by z cube. Therefore now we find out third derivative. So for that 2 as it is, derivative of 1 over z cube is minus 3 divided by z raised to 4. This is nothing but minus 6 divided by z raised to 4, and we are interested in the value of third derivative of phi at z equal to 2. So we find out value of phi triple dash at z equal to 2 will be equal to minus 6 divided by 2 raised to 4, or this we can rewrite as 2 into 3 and here 2 into 2 raised to 3. So therefore phi triple dash 2 will be equal to minus 3 divided by 8. So now we substitute this here, and we obtain residue of f of z at z equal to 2 equal to 1 by 3 factorial into phi triple dash 2. So therefore residue of f of z at z equal to 2 equal to 1 by 3 factorial phi triple dash 2, which is minus 3 by 8. So this is going to be minus, here we can write 3 factorial equal to 6. We take negative sign outside, and this is going to be, here 3 will cancel out, minus 1 by 16. So this we can denote by B1. So there is only one residue required for Cauchy's residue theorem here, because f of z has only one singular point, which is z equal to 2 and which is inside this circle mod z minus 2 equal to 1. So now we consider Cauchy's residue theorem. By Cauchy's residue theorem, integral of f of z along this circle, this is equal to 2 pi I times sum of residues of f of z. There is only one residue here, which is denoted by B1, and value of B1 is minus 1 by 16, which we substitute here, and here 2 will cancel out, and we have minus pi I times divided by 8. So therefore integral of the function 1 over z times z minus 2 raised to 4 along this circle is nothing but minus pi I divided by 8. So here we have to remember Cauchy's residue theorem. Also we have to remember this result, that if f of z can be written as phi of z over z minus z0 to the power m, then f of z has a pole of order m at this point z0, and residue of f of z at z equal to z0 will be equal to value of m minus 1th derivative of phi at z0 divided by m minus 1 factorial. So in our case value of m was 4, so we have taken m equal to 4 and we calculate third derivative of phi, and z0 was 2. So we have used this result as well as Cauchy's residue theorem. So in this way we can easily evaluate some complex integrals if they satisfy the hypothesis of Cauchy's residue theorem. So this is all about this session. I hope you like it. Thank you very much.